All right, so this is your first video lesson here. If this works out, maybe we'll try using this more often. But what I want you to do here is feel free to pause me, fast forward me, rewind me, whatever you need to do to make sure you get the most out of this lesson. That's kind of the purpose of this. If you're falling asleep in class because I'm moving too slow, well, with this video, you should be able to skip ahead to the like the tougher sort of examples. So that's sort of the idea behind this lesson. So we're looking at solving linear and quadratic systems. So if you think about the meaning of these two words, linear just means a line, quadratic means a parabola. So what we're going to be looking at today is we're going to have quadratic functions like this, and we're also going to have a linear function. And what we're looking for is sort of the points of intersection of those two functions. So that's going to be the main purpose of this video lesson. Okay, so looking at a linear function and a quadratic function, we have three possibilities for intersections. Now, the first possibility, the first scenario, is that these two functions intersect at 2 points. Okay, when a linear function and a quadratic function intersect at 2 points, we call the line a secant line. Okay, so the line is a secant. Okay, the linear function and a quadratic function, they could also intersect at only 1 point. Okay, and what we call this scenario is the line is a tangent line. Okay, and that word tangent, if you were just to look up the English definition, tangent just means next to or against. So 1 point, if there's 1 point of intersection, the line happens to lie tangent to the quadratic, or it's just touching the quadratic. Okay, and the last scenario is never. So the line and the parabola just simply do not intersect. Okay, so what I've got here, and I've just graphed this on the graphing calculator, which you can find on your Mac. I've graphed these three scenarios. So hopefully you can see that okay. So what I have here is my quadratic. This is my quadratic function. And I've graphed three separate linear functions. Each one represents one of the three scenarios. So our first scenario is represented by this green line. Okay, so I have a line that intersects this quadratic at 2 points. 1 point there, 1 point there. That makes this line a secant line. Okay, so scenario number 2 is our line happens to just be tangent to the curve. Okay, so it intersects at 1 point right there. That's our second scenario. Now, our third scenario, our line does not intersect with our quadratic function. So you can see this line is over here. No matter what happens, it's not going to intersect our quadratic. Our quadratic goes forever in this direction. Our line continues in this direction and that direction. There's no way that those two functions will ever intersect. So these are the three scenarios that are possible for this topic. All right, so what we're going to do is just kind of examine those today. Okay, so now that we've looked at the three scenarios that we can have for the intersection of a linear and a quadratic function, what we want to do is sort of examine the mathematics behind each scenario. So we're going to have three scenarios here, which we've talked about. What we want to do first, though, is take a look at our discriminant. Okay, so what I have here is just the discriminant can be used to determine whether the line intersects with the quadratic function never, once, or twice. Okay, so you'll recall from previous lessons that the discriminant is equal to b squared minus 4ac. So that's going to be the key to determining these points of intersection algebraically as opposed to graphically. Okay, so let's just take a look at these three scenarios. Okay, so scenario one, if you'll recall, was when we have 2 points of intersection between our linear function and our quadratic function. Now, this is going to happen when our discriminant is greater than 0. Okay, so we say that our system has 2 points of intersection, or 2 solutions. We could also call it intersections. Okay. Now this isn't much different than our discriminant when we looked at the number of solutions a quadratic has. If the discriminant was greater than 0, we knew that we had 2 solutions. Okay, the same thing goes for our discriminant when we're looking at the point of intersection of a linear function and a quadratic function. So that's scenario 1. Okay, scenario 2, if you'll recall, was that we have exactly 1 point of intersection. Okay, and similarly to when we're using the discriminant for quadratics, this happens when the discriminant is equal to 0. So we can say the system has exactly 1 intersection. Okay, and lastly, the last scenario was when we have no solutions. Okay, and that just leaves us when the discriminant is less than 0. Okay, our system has no intersection. Okay, and this is the case where the line and the quadratic do not intersect. Okay, so if we were to factor or use the quadratic formula, that will tell us the actual values for our point of intersection. So if we factor our system or we use our quadratic formula on our system, we'll obtain the x values of the points of intersection. Okay, so let's look at an example here. What I'm asking is, how many points of intersection do the linear and quadratic functions have? Okay, so for part A here, I've got 2 functions here. I've got a y equals a quadratic and y equals a line. Okay, so what I want to do is somehow determine the number of points of intersection here. And what I'm going to do is do this algebraically. So the first thing I do is I set the 2 functions equal to each other. Okay, this is going to allow me to eliminate the y variable. Okay, so I'm going to take my quadratic and set it equal to my line. Okay, when these 2 functions are equal to each other, I know that I've got a point of intersection. So what I want to do is set them equal to each other and check the discriminant, and that's going to tell me how many points of intersection I happen to have. Okay, so that's your first step. Next, what we want to do is collect like terms. We want to simplify this expression a little bit. Okay, so in order to do that, what I'm going to do is I'm going to move this 5x over to the other side, okay, because I know that 5x and negative 15x are like terms. Okay, I also know that 20 and negative 4 are like terms, so I'm going to bring that over to the other side as well, and I'm going to collect it with the 20. Okay, so that's my next step here. So my 4x squared doesn't go anywhere. I'm going to move my 5x over to the other side. The 5x becomes negative when I move it over to the other side. Okay, so I end up with negative 20x. I have 20 on this side. When I bring the negative 4 over, the negative 4 becomes positive. So I actually have 24. All right, and on the right side, I have 0. I took everything over to the other side of the equation. I no longer have a term on the right-hand side. Okay, so that was step one. All right, step two is to find the discriminant. Okay, now remember the discriminant is b squared minus 4ac. Okay, and we want to check what happens when we sub in our values from our new equation for our system. Okay, this equation contains both our quadratic and our linear functions. Okay, so I'm going to take the values from this this new system and I'm going to substitute them in. Okay, I know that a is 4, I know that b is negative 20, and I know that c is 24. Okay, make sure you take the signs. So I'm going to sub in 20, so I have 20 squared. I'm going to sub in 4, so I've got negative 4 times 4, and I've got 24. Okay, so the idea here is we want to check what our discriminant happens to be. Okay, so what we need to do is use our calculator here, or if you're lucky, you can do this in your head. I certainly don't feel like it. If we punch this into our calculator and we've done it correctly, we should get 16. Okay, now if we reflect on our previous slide, we know that because our discriminant is greater than 0, okay, 16 is a positive number. Because this is greater than 0, we have 2 intersections. In our system. So taking a look at part B for this example, we're being asked to determine the coordinates of the points of intersection, which we know from the previous example that we have 2 points of intersection. Now looking back at our note, we know we can either factor this particular equation or use the quadratic formula in order to find our x coordinates for our points of intersection. And remember, I'm using what I got as a result of setting the line and the quadratic equal to each other. I want to factor or use the quadratic formula on this particular function. So in this case, I'm actually going to factor. I find this to be quite an easy function to factor. Okay, now I'm not going to go through the steps for factoring in depth. If you are still having trouble, please come see me or check back at your notes for factoring assistance. But we should get something like this once we factor. Now, in order to get the x coordinates, what I want to do is set each bracket here equal to 0. Remember, I dismiss 4 because 4 will never be equal to 0. When I solve for x here, I get x equals 3 and x equals 2. Okay, so what I want to do next is take these and sub them into one of the original equations. If you look back at the previous page, we had equation number 1 was a line. That's probably going to be the easier equation to work with in this situation. Remember, we always want to make less work for ourselves. So what I'm going to do is just sub in x equals 3 into this line, and I'm also going to sub in x equals 2 into this line. Okay, and I'm just going to simplify here. I get 15 minus 4, which I know to be 11, and I get 10 minus 4, which I know to be 6. Okay, so therefore, our points of intersection are 3, 11 from here, and we know 2, 6 is also a point of intersection. Okay, and I simplify that by writing POI for point of intersection. Okay, now if we take a look at this graph, this is our quadratic function here, and this is our linear function in red. Okay, now these are the points of intersection which I just found using this method, and if we look at our graph, we can confirm graphically that those in fact are the points of intersection. Okay, so one last example here. This is certainly a more tricky, sort of more involved problem. Definitely going to see one of these in your homework, maybe on a test or a quiz coming up. We've got a line with a slope of 2, and we know that it's tangent to the quadratic function y equals 2x squared plus 4x minus 1. And they're asking what the y-intercept of the line is. Once you have the y-intercept, they also want you to write the equation of the line in slope and intercept form. Okay, so this problem is certainly more involved. So what I've done here is written up the steps for you. Simply follow along with these, and it should become clear as we work through it. So remember, tangent. This word tangent means touching the curve of the quadratic function. If you look back at the beginning of the lesson, we sort of defined that word. That's going to be the key to this problem. What we want to do is follow the steps right here. So we've got step 1, which says write an equation for the line where b represents the y-intercept. Okay. Now I know that equations can be written in the form y equals mx plus b. Okay, and what I want to do here is use the information given in the problem to sort of fill in this line. So I know the slope is given as 2, so I can write 2x. I don't know what b is, but I'm going to just call that the y-intercept as b there in our equation. Okay, so that's step 1. So let's take a look at step 2 here. Okay, step 2 just says eliminate y by setting the two functions equal to each other. And then we're going to simplify by collecting like terms. Okay, so really what we have here is sort of the same sort of problem that we had in the last example. We've got a quadratic and a line. So what we're going to do is set those equal to each other. And I'm going to do that now. So I've got my quadratic. I'm going to set that equal to this linear function. Okay, and I'm going to do the same thing I did in the last problem where I collect my like terms. And I know that 4x and 2x are like terms. Okay, I know that -1 and this b, remember b is just a number, so I know that these are in fact like terms. So I'm going to bring everything over to the other side and sort of collect my like terms and simplify. I know if I bring 2x over to the other side, I subtract 2x, so this just becomes 2x. I still have -1 here, and I'm going to subtract b as well, and I know that's going to be equal to 0. So that is my simplified new expression. Okay. Now step 3, this is where it's going to get a little bit confusing because we have this weird expression with a b. But what we're going to do is we're going to use our discriminant, and we know that there is only going to be one root here, and we know that because our problem tells us that this line is tangent to the quadratic function, and tangent lines only have one intersection point with the quadratic. Okay, so what we're going to do is just take what we have here and sub it into our discriminant formula. Okay, so this is going to be A, this will be B, and this is the weird part. This whole portion here is considered C. Okay, so we're just going to use that as our C term. Okay, so what we do is we say we know b squared is going to be 2 squared. We're subtracting 4 times 2, and then we're multiplying by this bizarre -1 minus b term. Okay, and we know that it's going to be equal to 0 because there is only one root for this particular system. Okay, so if I just clean this up a little bit, I know I've got 4 minus 8 times -1 minus b. Okay, all my goal here is just to solve for b, right? I want to get the y-intercept. So I'm just going to expand this -8 into the brackets. So I should get positive 8, and I should get plus 8b equal to 0. Okay, 4 plus 8, I know that to be 12. I've got 8b still. Okay, and I just want to solve for b. So I know that b is going to be equal to -12 over 8. Okay, now I know that -12 over 8 can be rewritten. I'm going to just call that -3 over 2. Okay, that's my y-intercept. Now to finish up this problem, I want to write the equation in y equals mx plus b form. I want to write it in slope-intercept form. I know the slope is 2 from above, and I know that my new y-intercept is negative 3 over 2. Okay, so that's sort of our final answer there. That's going to be the equation of the line that happens to be tangent to this quadratic function. Okay, so that's the end of the videos. Hopefully this worked out for you. So on Wednesday, what I'm going to do is give you some problems to work on in class using the note that you've developed as a result of these videos. Okay, so we'll see you in class.